Everyone, in this video lesson, we are going to measure the mass of an electron. We're actually not going to do it physically. We're going to talk about how it was done. But it's pretty cool. We have all the tools to actually see how this was done. So let's dive in. Let's get started. So here's the apparatus that J.J. Thomson used and in his experimental derivation of the mass of an electron. So I will note this apparatus and what we're going to be doing today can actually find the mass for any charged particle. But we're going to talk about how it was used to find the mass of an electron. Because remember, right now, we've looked at the history and understand how the charge on an electron and proton was discovered, the elementary charge. But right now, we don't know its mass. So let's talk about it. So we have this apparatus where there's both electric field plates, so parallel plates, and we have a coil of wire. And remember, one idea, so we've already talked about how a moving charge will experience a force in a magnetic field, but a converse of that is something that's also true, and hopefully you learned this in your grade 11 course, but you would have hopefully seen watching those review videos, is that a moving charge actually creates a magnetic field. And so this apparatus has two things: a parallel plates to make an electric field and a coils to make a magnetic field. So at any time, by turning on a switch, you can have just an electric field or just a magnetic field, or you can have both at the same time. So that's the idea behind this apparatus. So I'm actually going to just add a couple notes on here for you guys. So to start, we actually have, there's two sets of parallel plates. So we have a set of parallel plates here. To accelerate electrons. So we have these, you have this cathode, you heat it up, electrons are freed, and inside these parallel plates, the electrons are given some acceleration, and they leave the cathode ray tube with some kind of speed, at which point they enter this parallel plates coil combination. So if you can imagine, if you turn off the if you turn off the coils, so if there's no magnetic field, you're going to have two parallel plates. And if you recall our work with the inkjet printer, we know that the electron will be deflected somehow. So this point Y, we're just saying here, this point Y represents the deflection from applying some potential difference to the field plates. And so you can imagine, by varying the voltage, if you have a really high potential difference, really high voltage, you'll get lots of deflection. If you turn it down, you get a little bit of deflection. Turn it off, you get no deflection. So you can see there how by adjusting, you can make higher amounts of deflection. But if you turn the field plates off and you just have the coils going, and that makes a uniform magnetic field, well, now you can deflect the electrons in a different way, because we now know that a charged particle will experience a magnetic force and magnetic field. So you can deflect it another way using the magnetic field. Where is my cursor? If I had a dime for every time I've lost my cursor shooting this course, I probably have a couple bucks. So this point X represents the deflection from the magnetic field. So if you just have the parallel plates on, you get a deflection up. If you just turn the magnetic field on, you get a deflection down. Well, you can imagine if you had both, there'd be some balancing point where those two forces would be equal: an electric force deflecting up and magnetic force deflecting down. And if you could balance those guys, your electron would travel in a straight line to point Z. So that's kind of the setup for the apparatus. So let's talk about the derivation. So here, this is our starting point, actually. Our starting point is we're going to imagine the electric field plates. Imagine the field plates are off. So turn the field plates off. So that means that we're going to have a magnetic force. And remember, it's going to give us some uniform circular motion because the force and velocity are always parallel. And we've already quantified the magnetic force. It's going to be equal to E. Remember, that's the charge, the size of charge on an electron. It's the elementary charge times its speed times the magnetic field strength. And FC is mv squared over r. We get some v's canceling. And so this is actually should look actually kind of similar to something we did in our last lesson. But here I'm actually going to just rearrange this a bit differently. We get that E over m. So I'm dividing the m, and I'm going to divide the b over, equals v over br. So think about what this means for a second. So remember that at the time of this experiment, E was known, right? We know the charge on an electron. We don't know the mass on an electron. But what this is saying is if you could figure out the speed, this magnetic field, and this radius, then you could determine the mass, right? Since E is known, if V, B, and R were known, we could find M. So B and R are actually easy to find. So if you have the coils and have the apparatus, you can just measure all that stuff directly. But getting the speed, not so obvious. So this brings us to our second point. So to determine the electron speed, Thomson used some parallel plates. So when there's no current in the coils, so the electron is deflected, as we've talked about, by applying a potential difference to the plates. So now we're turning off the magnetic field. And you can adjust the potential in the plates so the deflection upward is exactly the deflection downwards. And you get them two being equal to each other. So at some point, by just varying the knobs, you can make these two things balance. Fm equals Fe. So as we talked about in our diagram, then if those two things are balanced, we're going to hit point Z in this diagram. All right, well, let's plug some stuff in. Fm, we know how to get that. It's EVB. Ye, charge on an electron. Why no sine stuff? Because we're assuming that theta is equal to 90 degrees. And the electric force, we know how to calculate that too, right? Electric force, remember, just like Fg equals mg, Fe equals Q epsilon. And the charge here is the elementary charge, E. And the field strength, because we're in two parallel plates, the field strength is epsilon. And so you can see the charges cancel out, and we can get an expression for V. V equals epsilon over B. So if we go back to what we had for the ratio of charge to mass, remember we had V over BR. Well, now we can replace V with epsilon over B, and this is times 1 over BR. So we get E over M equals epsilon over B squared R. So we're getting closer. If we knew, and we know the charge, we know the field strength, we know R. If we could figure out the field strength inside the parallel plates, then we could find out. We'd have everything we need. So we've got our derivation for E over M. If we know epsilon, we know magnetic field strength, we know R, we can calculate this ratio. So for an electron, and then so I should say that Thomson did this experiment over and over and over again. So with a certain with a certain, so he could vary, so he could keep the electric field the same. So he could keep the voltage the same and vary the magnetic field. And so he would get a different radius of circular motion, and that all could be measured, and he'd get a value for E over M. And then he would change the magnetic field again, get a new R, calculate E over M. And then, but he could also keep the field strength, the magnetic field strength the same, and adjust the voltage and see what the new R is, and get a different value for E over M. And so what he found was, in all these combinations, the value for E over M was similar. The accepted value, as he did this experiment over and over and over and changed B, changed epsilon, what he got was, and the accepted value is this. The ratio of charge to M for an electron was 1.76 times 10 to the 11. And that is coulombs per kilogram. So in his experiment, all the varying and adjusting he does, he always gets E over M being 1.76 times 10 to the 11. So that's pretty cool. So we can use this ratio to find the mass of an electron. So the mass of an electron would then be E divided by this 1.76 times 10 to the 11. And we know E, 1.6 times 10 to the minus 19, divided by 1.76 times 10 to the 11. And if you give this a go, and actually just, I might throw in 1.602 here just to get a more accurate value. 19 divided by 1.76, 10 to the power 11. So we get our familiar was about 9.1 times 10 to the minus 31 kilograms. So I think that's extremely neat. By setting up this clever apparatus where you can vary the voltage, you can vary the electric field, Thomson could calculate this value over and over and over again for different values for epsilon, for B, etc. But it always came out to 1.76 times 10 to the 11, allowing him to find the mass of an electron. So that's pretty neat. Now, this was to find the mass of an electron, but Thomson's technique can be used to determine the mass of any charged particle. So this could be helpful for, if you could get a charge on some just atom of some element. So if you can make it an ion, either gain an electron or lose an electron, you could find the mass of that charged particle in the same way. So Thomson's technique is used all the time to measure the mass of small particles. So I'm just going to make a little derivation with you guys to show how we can do that. So our starting point will be this: Q over M equals epsilon over B squared R. Now this is the exact same formula that we used before. It's just now we're not using the electron. So instead of E, I'll have Q there. And I'm going to rearrange that. So that means you can get the mass of any charged particle. So just doing some rearranging, we bring the mass up, and multiply. Is that right? Multiply the B squared over. Yeah. So we get Q times B squared times R divided by the field strength. Now, we can actually get this field strength. We're going to go a bit further than we did last time. So just as an aside here, remember that delta V is equal to epsilon times R, field strength times R. And so in our equation there, we have epsilon on the bottom, right? So we have like 1 over epsilon. This is equal to R over delta V. I'm going to plug that in here. So Q B squared over epsilon, B squared R. I might just actually rewrite that just to make it more clear. So we have QB squared R, QB squared R, but the field strength is given by R over delta V, and you get this nice expression for Q over M, that ratio. It's equal to, or sorry, nice expression for the mass. It's equal to Q B squared R squared over delta V. So if you knew the charge, which often you do, if it's an ion of something, you know that that's a deficit of 2 electrons or 3 electrons or an excess, and that just depends on the element. So I actually stopped taking chemistry in grade 11, but I know enough that each element has its preferred ions that it's in. So it's actually not hard to get the charge. Again, it's not hard to get the field strength if you know the magnetic field strength, and you can measure the radius of circular motion, and you can measure the delta V. So if you fire in a charged particle and you know the charge, you adjust B, you adjust V, and if you just measure the radius of circular motion, you can get the mass of the charged particle. So that's really, really, really cool that we can find the mass of very small things this way, just by firing them through this apparatus and measuring that radius of the circular motion. So